All right, level 2 physics, electricity, we're working on 2022. Two parallel plates are set up 2.2 millimeters apart with a voltage of 15 volts between them. Show that the electric field strength between the plates is 6.8 times 10 to the power of 3 volts per meter. Pause this video, have a look at your formula sheet. What equation do you need to use to find the electric field strength? Use the values that we've been given and then come back and play the video. Assuming that you've gone and done that, let's have a look at what formula you should have picked. E equals V over D. You should have plugged in voltage, which is 15, over distance, which is 0.0022 meters. So you should have converted the millimeters to meters by dividing it by 1,000. And you should have gotten this answer here for a nice, easy, achieved. Don't forget your units as well. Next question. An electron at rest is released from a negative plate and accelerates towards a positive plate. Calculate the maximum speed of the electron when it reaches the positive plate. So I'm just going to do a bit of a drawing here. Pretend this is the positive plate here, and this right here is the negative plate. And this is the electron. So the electron, we know that electrons are negatively charged. My bad, let me just swap this around. So we've got the negative plate here and then the positive plate here. That will make more sense now. So we know that electrons are negatively charged, and so it starts off, when it's at the negative plate, it starts off with a whole lot of potential energy, okay? Because of electrostatic force, it is being pulled down towards the positive plate, okay? And so while it moves to the positive plate, which is oppositely charged to itself, that EP, that potential energy, is turning into kinetic energy. So by the time it fully reaches the positive plate, all of that EP has been converted and equals the kinetic energy. It's been transformed. We know that it has to move towards a positive plate because opposites attract, and that is due to electrostatic force. So bearing that background information, how are we going to work out velocity, how fast it's moving from the negative end of the plate to the positive plate? Well, if you look at your formula sheet, you need to pick an equation that has velocity in it, and that's going to help us find out what we need to. So take a pause, see if you can figure it out. When you come back, let's have a look at what you should have picked. Assuming that you've gone and done that, this is the equation that you should have picked because it's got velocity in it. We know that EK is equal to EQD, which is potential energy, okay? EK is equal to potential energy, and I've written that here. So because of that, what I'm going to do first is I'm first going to work out the potential energy, and then I'm going to substitute that in to this kinetic energy equation. All right, so by figuring out what EP is, that's essentially going to be the same as EK because all of that energy is transferred to EK. So this is the equation to figure out what the potential energy was. And so I've got the electric field strength. I've got the electric field strength times the charge, which is given to you in your formula sheet, times the distance of the plates that this charge is moving through. Putting that all into your calculator, you should get this value here. So this is how much energy that electron stored, and it's been fully converted into EK as it moves to the oppositely charged plate. And so I've got energy over here, okay, which essentially is EK and EP, equals half mv squared. What is the mass? It's been given to you, okay, on your formula sheet, and we're rearranging to find v squared. Before I rearrange, let me simplify these values here, a half times the mass, and I get this value here. Now, with a bit of algebra, I can get rid of this value to make V, velocity, the star of the show, because that's what we want to figure out. And so to get rid of times mass, I have to divide this whole side by the mass, okay, times half as well, okay? So to get rid of times, you divide, and you have to do the same to the other side. What you're left with is V squared equals all of this value here. That's what V squared, that's what V squared equals, okay? And we want to find what V equals, not V squared. So to get rid of the square, you simply take the square root of both sides, and you should get this velocity value in meters per second. Hopefully that made sense. It's just a bit of algebra. If this is something that you need to work on, make sure you spend some time getting strong with your algebra skills. It makes your life a whole lot easier for physics. That was worth a merit. Please don't forget your units. Now we can move on to part C. A student states that increasing the distance between plates while keeping the voltage the same will mean that the electron released from rest at the negative plate is accelerating over a longer distance and will therefore reach a higher speed than in part B when it reaches the positive plate. That was a mouthful. Basically what they're saying is that by increasing the distance between the plates, okay, they're able to ensure that the electron's traveling at a faster speed over that time and distance, okay? So we need to explain why they're wrong, basically. And so I want you to think about it. I've got an equation that involves both voltage and distance and electric field strength, okay? And so have a think and then come back and play the video. Assuming that you've done that, if you increase the distance, okay, this decreases the electric field strength according to this equation, because electric field strength and distance are inversely proportional. If you increase one, the other one decreases. So if you increase the distance and it's reducing the electric field strength, you might be tempted to think that this actually slows down the electron. But I want you to understand that this is not linked to the energy that the electron has, okay? And so because the EP is not linked to the increase of distance between the plates, the speed actually stays the same. These variables aren't really linked, okay? And so that understanding that is worth a merit. Now, the second part to part C is asking, state one thing that could be done to increase the maximum speed of the electron, okay? And so, one thing that you can do to increase the speed of an electron is to increase the voltage supplied by the battery or the voltage source, okay? And so that is something that can be done to increase the maximum speed of the electron. Okay, and the reason why is because when you increase the voltage, you're basically supplying more energy within the field, and so it increases in velocity. More of that energy is converted to more kinetic energy and hence greater velocity. Part D. The diagram below shows the electric field between a set of parallel plates, D meters apart and V volts between them, okay? The distance between the plates is now doubled, as you can see here, and the voltage between them is halved. What happens to the strength of the electric field? Your answer should include a number. Okay, so let's look at electric field strength and what happens as a result of doubling the distance and halving the volts. Okay, so I want to start off by explaining to you what's going on in this equation. So as you can see here, we've got the equation for electric field strength, and I want to talk about a few relationships. So if we're looking at the relationship between distance and electric field strength, this is an inverse relationship. Distance is inversely proportional to electric field strength. What does that mean? Well, if you increase the distance, this results in a decrease electric field strength. Similarly, if you were to decrease the distance, this would result in an increased electric field strength. That's what it means by an inverse proportional relationship, okay? And so if we were to increase the distance by double, okay, if we were to increase the distance so it's 2d, okay, that means the electric field strength would decrease by that same amount. So essentially, it would decrease by a factor of 2, okay? And I want to kind of draw that out. And so if we have electric field strength, okay, and we start off with 1 unit of that, and if we have 1 unit of distance, okay, and we decide to double that distance, now we've got 2 units of distance, okay? We've doubled it. So because distance is inversely proportional to electric field strength, what would happen to the electric field strength? Well, it would essentially decrease in its strength, okay? So it's twice as weak as what it was, okay? So if we started off with 1 unit, okay, of electric field strength, and we were to, say, divide it by 2, because the opposite of times 2 is divide by 2, would actually be left with, I tried to draw it before, but it wasn't very accurate, a half. Okay, so we've got 1, and then we've divided it by a factor of 2, and then we get 0.5. Okay? And then in the case of distance, let me make that a little bit more clear. We started off with 1, and we've doubled it to get 2. Okay? So as a result of doubling the distance, okay, the electric field strength decreases by this much, by the same amount that we increase the distance by, and we get half of the original electric field strength. Okay, but there's another thing going on here. We've got the voltage, which is actually halving halved as well, okay? So it's being halved, and so how does that impact the electric field strength? Well, what is the relationship with voltage and electric field strength? In this case, it is directly proportional. What does that mean? Well, if we increase the voltage, we get an increase in electric field strength. Similarly, if we decrease the voltage, we get a decrease in electric field strength by the same amount. So if we've halved the voltage, let me draw it here. This is voltage, okay, and this is electric field strength, okay. And in this instance, our electric field strength is already at half, okay. And so, if we've got the voltage and we halve it, what we get is 0.5% voltage. Not percent, sorry. We get half the voltage, so 0.5 units of voltage. So if we decrease or divide the voltage by 2, or halve it, we have to do the same to the electric field strength because it is directly proportional. And so what we're left with, if this was 0.5 and we halve 0.5, we are left with a quarter, which is 0.25. Okay? So in total, because we have, first of all, doubled the distance, we have to reduce the electric field strength by that amount. Because we have halved the voltage, we have to reduce the electric field strength even more by that amount that we've reduced the voltage by. So hopefully that makes sense. And when we talk about it, this is what I've written. Electric field strength is represented, let me get my pointer. Electric field strength is represented by E equals V over D. Since distance is inversely proportional to E, if D is increased, E will decrease. Velocity is directly proportional to E. So if it increases or decreases, so will the electric field strength. Therefore, if D is doubled to 2D, then electric field strength will decrease by a factor of 2. So it will become 0.5. Since voltage is halved, E will decrease by a factor of 2 again. So what we get is E, electric field strength, is in total a quarter of its original value. Okay, hopefully that makes sense. Let's move on to the next part. Using the same scale, draw in the field lines on the diagram below to show a new electric field between the plates. Okay, so what we have here is the original, and it's not been doubled, it's not been altered, and so we count the number of electric field lines. So we've got 12. This is the original electric field strength, okay? And so the more electric field lines there are, shows greater strength of electric field. However, when the electric field or the plate's distance is doubled, okay, and the voltage is halved, what we get is a different looking diagram, okay? Because we discussed that when the distance is altered and the voltage is altered, the electric field strength is a quarter of its original strength. We know that a quarter of 12 is 3. And so we have 3 field lines to show what has happened to the strength of the electric field. And that is that question done. This is what your drawing would look like, and this is worth an excellence. Hopefully that made sense. If it doesn't, please email me and we'll get in touch. Otherwise, I'll see you for the next tutorial.